All right, hopefully all of you are still with me as we're continuing our journey deeper into the solar system. We've covered the Earth. We looked at the moon and Mercury because there are many similarities between those two bodies. And there are differences as well. So that's something I've asked you to reflect on a little bit to figure out how exactly they could be similar and different. But on balance, you could say that the similarities outweigh the differences, and so it makes sense to club them together a little bit when studying the moon and Mercury. Now, moving on to what most people would consider the more interesting planets. Why are these more interesting? Well, on the one side, Venus, which is closer to the Sun, is considered Earth's twin in many ways because its mass, its radius, and so on are roughly the same as the Earth's. And it's also not that much further away from closer into the Sun than the Earth is. The Earth is roughly at 1 AU. Venus is about 70% that distance. And as you can see, it's 95% Earth diameter, 80% Earth mass. But there are obviously some key differences, as I've hinted in past lectures, and as you might have read in the textbook as well. The surface temperature is insane when we did material on greenhouse gases and the effect that they have on surface temperatures. Venus has a surface temperature hot enough to melt metals like lead. It has an atmospheric pressure that's 90 times Earth's atmospheric pressure. So, not exactly a twin in that sense, but physically, yes, and there are also some intriguing similarities with the Earth that are worth paying attention to. Because of its extreme inhospitability, we have not explored it nearly as much as we have explored Mars. So we'll get into the missions to Venus, but in the past 30 years, we've only sent about 3 missions to Venus, and you could argue that it's crying out for way more exploration than Mars is to some extent. And for Mars, we've probably sent, dozens in the last 30 years or so. Not all of them have made it because getting to Mars is still incredibly hard despite all the advances we've made since satellite exploration has begun. Speaking of Mars, it's of the terrestrial planets, it's the only other one that has moons, which are 2 smallish asteroids. It's 1.5 times further away from the Sun than the Earth is, so it's at about 1.5 AU. It's much smaller than the Earth, 50% Earth diameter, 10% of the mass. The atmosphere is 1% of Earth's atmospheric density, so not exactly planet B. And I'll put up a TED Talk about why there is no real planet B in our solar system so far, and none that we've discovered amongst other exoplanetary systems. That may change, obviously. You'll see the most Earth-like planet discovered to date reliably showing up in the news maybe anywhere from once to 6 times a year, possibly, and maybe even more as the TESS satellite mission starts gathering more data. Anyway, so Venus is the closest planet to us, and it shines beautifully in the evening sky. It was called the evening star or the morning star because it's closer to the sun. So it's usually most visible around sunset and sunrise, similar to Mercury. We looked at the elongation of Mercury above and below the horizon and why it was tough to observe for so long. And Mars is the next closest planet. So that's partly why Venus and Mars have captured our imaginations and evoked such a lot of fascination. Venus has these amazing clouds that mask the surface completely, so it's kind of mysterious and beguiling, beautiful to look at. Mars, we can, of course, see right through to the surface, and it's this crazy red color that is unlike any other planet that we have in the solar system. And of course, they're being the closest, they are in theory the easiest to get to send satellites and rovers and landers and so on. Of the two, Venus has slightly more circular orbit than Mars. Mars has an eccentric orbit. We hinted at that early on when we talked about the effects of eccentricity on seasons. And in noting that Mars has more extreme seasons in one hemisphere versus the other because it tends to be at perihelion, when I forget the exact sequence, but basically the winters in one hemisphere are more extreme than the winters in the other, and the summers as well, because of the changing distance from the sun as Mars goes around its orbit. So Mars has the next most eccentric orbit after Mercury, and that affects its seasons to some extent. So here's some data on Venus. Like I said, it's similar to Earth in its size, in its mass, in its average density, and the surface gravity. So gravity, if you remember, depends only on the masses of the two bodies and the distance. So because Venus has a similar radius and a similar mass, the surface gravity would be the same. Now, there's also the atmospheric pressure, which is a completely different thing, which is way higher than on Earth. So because Venus has a slightly lower radius and a slightly lower mass on it, you would basically end up weighing about 10% less as a result of gravity alone. So the gravitational force would be 10% less on Venus. But because the atmospheric pressure is so high, you would be more buoyant on Venus as well. And so that would cause yet another 10% decrease in your weight as well. So if you had a weighing scale on Venus and you were standing on it, now whether or not you can withstand that crushing atmosphere is another thing, but your weight would be 20% lower. So there's two different things going on here. There's the buoyancy to the atmosphere. It's like if you take a ball and submerge it underwater, even if you take it, several meters deep, you could take it a few feet deep and the ball will be fine. But you could feel a force pushing the ball back up because it's filled with air. But if you go further and further and further down, at some point the ball will start getting compressed because of the weight of water above it. And so so if you walked out of your spaceship on Venus, you could briefly feel good about the fact that you weigh 20% less, and then you would get crushed. So bittersweet, I guess, is the way to think about it. As you can see from this photo here, I think it's in the UV or near enough to visible that the surface is covered with these highly reflective clouds. They conceal features from Earth-based observers, so no matter what kind of telescope you use from the Earth, it's hard to pierce beneath Venus's clouds and get a sense of what the surface looks like, unlike Mars, where you can actually get photos off the surface, and pretty nice ones from things like the Hubble Space Telescope or ground-based telescopes and so on. But we still needed to get up close because it's a smallish planet, and there's interesting stuff that you can only study when you're there, like the geology and whether or not there's water or life and so on. So Venus's period of revolution is about 220 days or so, 224 days, but its rotation rate is extremely slow. In fact, its rotation rate, is slower than its revolution rate. So 240 days basically going around on its axis once, versus 220-ish days to go around the sun once. And the other thing is it rotates retrograde. It rotates retrograde, not revolves retrograde. It revolves in the same direction as all the other planets, which is counterclockwise if you were to look from the vantage point of the Earth's North Pole above the solar system. But it rotates in a clockwise direction, and much, much slower than a lot of the planets out there. Probably the slowest planet in terms of rotation. However, the other amazing thing about this is it is the hottest planet in the system. Mercury is 1/2 the distance to the sun, gets 4 times the solar energy, yet Venus has the highest surface temperatures and has higher surface temperatures than Mercury. And that is entirely it's due to the fact that it's the second closest planet to the sun, but the rest of it is entirely due to the atmosphere, which is this crazy hellish greenhouse atmosphere filled with carbon dioxide that's trapping a lot of heat close to the surface and up above in the atmosphere as well. So like I said, Venus rotates very slowly in a retrograde direction. The solar day, again, is different from the rotation period. We went through this calculation with Mercury as well, where it has this unique 3:2 ratio, where it does 3 rotations for every 2 revolutions, And again, because of the weirdness, which is nearly 1:1, almost like the moon going around the Earth between its rotation and revolution, it takes double. So it takes 240 days to complete a rotation period, which would be a sidereal day. So if you were to pick a distant star and use that as a reference for when that star is, when it's directly overhead one night to when it's back directly overhead, if you can actually see through the atmosphere to see that star, then the sidereal day would be 240 Earth days. However, a solar day would be 117, or less than half that, where if you start with the sun directly overhead, and that you can most likely see, and then wait for it to come back to being directly overhead, you basically have to wait 117 Earth days. So that is the solar day is 117 days. The sidereal day, or one rotation around its axis, is 243 days. And the time taken to make one trip around the sun on its revolution is 225 days. So some fairly strange numbers, largely because of this clockwise rotation in the opposite direction, this really slow rotation as well. It'd be an interesting exercise for you to sit down and draw the diagram to figure out how you end up with a solar day that is so much shorter than the sidereal day. On Earth, the sidereal day is only about 4 minutes shorter than the solar day, but it's the opposite on Venus and way, way different as well. Okay. So like I said, the clouds reflect about 70% of the sunlight. The other consequence of the clockwise rotation is that the sun would appear to rise in the west and set in the east, which I don't really need to mention, I guess, now that you know all about rotation and what that does in terms of the motion of the celestial sphere. Let's see. About half the spacecraft, let's say 50 of them, roughly, have been sent, half the spacecraft that have been sent to Venus, about 50 of them, have failed. So again, it's tough to get through. There's a bunch that have landed. The Soviets have landed about 10 landers, and I think the longest any one of them lasted was about 20 minutes. So for a while, the Soviet Union was peppering Venus with these landers, but after a while, I think they gave up just because they just don't last that long. And finally, the magnetic field, because of its slow rotation, I'll ask you to guess over here. Is it Earth's twin, so probably has similar core, mantle, crust, and so on. Maybe even has a liquid iron crust, core. Part of the core may be liquid iron as well, but we don't have P and S wave data to actually completely verify that. But one clue that we do have is the magnetic field. And with slow rotation, I'm going to ask you to guess. Do you think that magnetic field is stronger than the Earth's, weaker than the Earth's, or about the same as the Earth? Okay, in addition to the fact that it is completely covered with clouds, like Mercury, but less of an issue, is the fact that it is never far from the sun. So you have to, if you're doing Earth-based observations of Venus, which Galileo did with his telescope, by the way, and that's what brought even more proof to bring down Ptolemy's geocentric model of the universe and replace it with a heliocentric one of the solar system. Basically, he saw phases on Venus, and you can see it even with the naked eye. It's a lovely sight, and with maybe binoculars or a cheap telescope, you'd be able to see that it has phases every now and then when it is up in the sky. But it's never more than about 50 degrees away from the sun in the sky. Unlike Mercury, which has two issues. One is the fact that it has a highly eccentric orbit, so sometimes it's 18 degrees away, sometimes it's 26 degrees away. And it's about, even at its maximum separation from the sun, it's about half the separation that Venus has at its greatest elongation. So tough to observe in general. Okay, quick review about terrestrial planets, because we're going to go over the same material. We learned that the terrestrial planets are all differentiated. Okay, so they were liquid at one point. As a result, they have a core where the densest material is, a mantle where there's the intermediate density material, and they have a crust, which is the lightest material, which is relatively metal-free compared to the core, for example, and much less dense. Not much less, but 3 grams per centimeter cube versus about 5.5. Yeah, it is much less dense. Okay. They all have evidence of geological activity at some point caused by interior heat left over from formation and radioactive decay. How quickly they lost that internal heat depends a lot on size, and how much, and the radioactive heat, whether it's powering geology today, depends also on size, and basically because it tells you how much stuff is inside the planet that should still be emanating heat that goes out to the exterior. Okay, some of the planets have magnetic fields. We realize Mercury has a magnetic field, the moon does not. So if you're keeping score, the Earth obviously has a magnetic field, which is why we have an atmosphere, which is why we have aurorae, all that stuff. The moon does not, so it's much less sheltered. Atmosphere, if it had one, has been stripped away. Mercury has a magnetic field. Interesting, because it's mostly core. Some 75% of its diameter is a metal-rich core, we think, and there is a magnetic field preventing, or which protects it a little bit from the solar wind. All right, and of course it requires the motion of metallic stuff inside the planet to be producing a magnetic field. Okay, then the main processes that shape surfaces, we talked about 4: impact cratering, volcanism, tectonics, and erosion. Erosion requires an atmosphere. The moon and Mercury don't really have one, so that knocks that out. Tectonics are depression, internal heat being released can deform the surface as the outer crust cracks and deforms. We saw evidence of that, some evidence of that on Mercury, and a little bit of evidence of that on the moon as well. And no plate tectonics, which is the entire crust moving around as a result of processes within the interior of the body. Volcanism. We've seen lots of evidence of volcanism. I mean, it's certainly there on Earth. We saw evidence on the moon with Maria, which is these black basaltic plains that have filled in with runny lava after impacts on only one side of the moon, which is kind of interesting. And we saw evidence of this on Mercury as well, where the smoother parts of Mercury are actually smoother than the moon, implying that it may have had volcanism going longer than the moon did because there's fewer craters. And of course, impact cratering. The moon and the Mercury have plenty of evidence of that. There's some on the Earth that we saw. The reason we're here is because of an impact crater, or at least the thing that impacted the Earth and wiped out the dinosaurs. And we're going to look at that on Mercury and Venus on Mars and Venus as well, to see how their surfaces have been shaped by these 4 processes. Mars and Venus both have atmospheres, so that basically means all 4 of these processes are in play. We cannot necessarily just dismiss any of them now, because there is now cause to believe that, we know for a fact they have atmospheres. We know for a fact there's changes in the wind and stuff moving around, so wind erosion features are certainly there. We're also going to look at whether water was present at any time in the past. There's no evidence of that being present now. There's ice on Mars, just like we found, surprisingly enough, on the moon and Mercury. On Venus, it's really too hot for any kind of ice to exist anywhere, because it's all well mixed, the atmosphere. It has a thick atmosphere that redistributes heat all around the planet. So there's no places like the shadowed basins of craters where you might have no sunlight hitting it or no atmosphere to warm it up. And so you can have pools of ice down there. Okay. Let's see. Taking an X-ray of the interiors of the planets, we noticed that both Mercury and the moon had different proportions of core to mantle and crust, where the moon had only 20% core, and Mercury was about 75% core by radius or diameter. The Earth is around 50% core. So that played into formation theories of Mercury and the moon as well. Now, Venus, being Earth's twin, seems to be, again, we don't have nearly as much definitive proof, seems to be of similar proportions to the Earth. So yet more support that it is Earth's twin. So we think there is a core which is around 50% of its diameter, the rest is mantle, most of the rest is mantle, and then there's a thin crust on top of it. We think the crust is mostly basalt or lava, like we find on the base on the ocean floor, maybe 6 to 12 miles thick, or 10 to 20 kilometers, and The iron core is about 6,000 kilometers in diameter. Venus has a diameter of about 12,000 kilometers, so that's 50% right there. Okay, Mars. Again, crust, mantle, core. Mostly mantle, and we know a lot more about its core. When we get to the lecture on Mars, we'll talk in more detail about what's inside Mars. But yeah, so nothing to sort of stand out and say, this doesn't quite look at... Oh, sorry, what am I saying? Mars, yes, it does. It seems to be mostly core and lithosphere and very little mantle. So when we get to Mars, we'll talk about that. So the lithosphere is pretty deep in Mars compared to Earth and Venus. So the dashed line that you see around those planets gives you an estimate of the lithosphere. So yeah, there's a crust that's about 30 miles thick on Mars. It's over basalt, 6 to 30 miles thick, whatever. Anyway, this is a lecture on Venus. We'll talk about Mars when we get to Mars. All right. So this time, so remember for the Moon and Mercury, I basically did the atmosphere part first because it was easy to dismiss. The answer was, is there an atmosphere? No. There's this thing called an exosphere. What is the exosphere? Okay, let's move on. We can't do that with Venus and Mars. Venus, as you know, already has a very, very significant atmosphere. And so we're going to deal with that in depth later on in this lecture. Mars has an atmosphere as well, so we're going to deal with that in depth when we do Mars as well. So let's start with the geology of Venus, where we're now going to talk about cratering, volcanism, tectonics, and erosion. And we'll also try and answer the question of whether Venus has or could have had plate tectonics now, because we know that there are certain unique features about the Earth that cause plate tectonics to happen. One of them is the fact that water is present to lubricate some of the movement of crustal plates below and above each other, especially at subduction zones and so on. All right. So back in the day, in the 60s and 70s or so, the Soviets seemed to have the right idea, where they said, okay, this is the closest planet. It's kind of interesting. We can't see a whole lot from it. Let's try and send something there so we can probe more about the interior. So it sent multiple probes that went into the atmosphere, 10 landers that landed on the surface, and I think the maximum might have been Venera 13 or something. Stayed alive was about 13 minutes or so. And this is what they saw. Not much cratering, these flat lava plains that look like they have been recently repaved, recent in the geological sense, meaning in the last 500 million years or so in the last 500 million years. So automatically, you may start asking yourself, okay, which of the four of cratering, volcanism, tectonics, and erosion, which of those might be the dominant process? All right, just looking at these pictures, take a guess. So it's a relatively young surface that seems to have been resurfaced. Which of those four processes allows you to completely resurface a process and wipe out traces of the other types of geological shaping? Okay? But to get a more global picture of Venus, poor pun again, we basically had to resort to sending spacecraft there and using radar to penetrate the clouds. Because like I said, this atmosphere is super thick. Earth's troposphere, for example, is 10 kilometers thick. Venus's is 50 kilometers thick. So 5 times as high. The lowest level of the atmosphere is 5 times thicker than that on Earth. And so it's very hard to basically send optical wavelengths. On Earth, as it is, you lose blue, for example, because it gets scattered out of the way. On Venus, by the time any kind of light or photons, except for the really long wavelength stuff, by the time it makes it through and comes back out again, it's mostly scattered, absorbed, and stuff like that. So this is an ultraviolet image. So this is the upper clouds or the outer clouds. They would be invisible at visible wavelengths. At visible wavelengths, you would basically just see kind of a shiny cue ball type of planet. And yeah, there's absolutely no hint of what the planet looks like underneath. So that's why we needed radar. All right? And we sent a mission called Magellan in the early 1990s. So it's still about 30 years on. And it basically went around the planet, sent radar waves bouncing through and back, and the atmosphere, fortunately, is transparent to those. So we sent them out, they bounce back, and you get an idea of what the topography underneath is. And that's the result is on the left, where the bright stuff is rough terrain. The dark stuff is smooth, kind of like, well, this has just been colorized that way. Anything that's red or white is higher. Anything that's, there's no blue over here. Maybe I'm talking about the next slide. Okay. And so it looks like, if you look at the slash of white across from lower left on the image on the left to the middle, it seems like a high, I'm going to say continent, but in quotes, surrounded by, again in quotes, lowlands or flatter, smoother areas. So automatically, with an Earth-centric perspective, you could be like, that kind of looks like continents and oceanic beds or something that could have existed at one point. So I'll ask you to hold that thought, and we'll figure out whether that might have been true or not. There's a bunch of mountainous regions that make up about a third of the Venusian surface. Say, unlike the Earth, well, it's roughly similar to the Earth, where land is about 30% and the ocean covers 70% of the Earth's surface. And so that's about a roughly 1/3-ish. So, similar. So there's mountain ranges that are almost 500 miles long. Some of them are 7 miles high. So Everest, for reference, is about 5 miles high. So these are, and of course, but it doesn't count from, say, the seabed up. Mauna Kea, for example, is, if you count from the seabed all the way to the top, is about 33,000 feet, which would make it about 6 or 7 miles tall. So that's the kind of height that you're talking about. The other problem with this radar, though, is that its resolution is extremely low. Because you're using, so remember, resolution was wavelength divided by diameter. So you have and the smaller number is better. So when you divide wavelength by diameter and you get a really small number, it means you have really good resolution. That means you can tell 2 points that are really close together apart as 2 separate points. Now, radio waves have really long wavelengths, so that's strike number 1. So wavelength divided by diameter, you're automatically going to get a large number because your wavelength is large. And the diameter, if you look at the satellite that's going around, it's a satellite. So you can't put a dish on it more than 1 or 2 meters wide because it just wouldn't fit in a rocket. And this was before we were unfolding dishes and stuff like that, like we're planning to do with the JWS, with the James Webb Space Telescope. So with wavelength being really long and diameter being really small, when you divide wavelength by diameter, you get a large number. So basically, each little pixel or each little point on this image on the left is 100 meters, which is the length of a soccer or a football field. So each little point is 1 football field long. So not really great in terms of how much we can tell apart so we can see big features like mountain ranges and lowlands and stuff like that, but we can't see the really small stuff. And there are 2 problems with it as well. We're planning to send landers back to Venus, but we need to know where to land them. And it's been 30 years since Magellan has been there. We just finished measuring or getting much tighter boundaries on Venus's rotation rate by doing a whole bunch of complex stuff, because you can't see the surface, unlike Mars, where you can just pick one feature, wait for Mars to turn, wait for that feature to come back into view, and you're like, aha, okay, that's how long it took for Mars to rotate. You can't do that with Venus, because you need to send something there, held it in place over Venus, sent a radio wave down, found a feature, then wait for the planet to go around and then do it again. So whatever. Wait 200 days for that to happen. So the point is that, again, this is now, okay, so this one now has, what was I going to say? Yes. Bright is rough, dark is smooth, red or white is high, and blue is low. So in this relief map of Venus you can actually, and here the resolution is even worse. On the previous picture it was 100 meters, here's it's 3 kilometers or so. Okay, oh, and the caption tells you what it is. All right, there's two so-called, oh wait, where was I? Yes, where to put a lander when you're landing on a place where you can't see the ground. You need to have, so in 1990, 30 years ago, Magellan told you, okay, this is where these features were at the time. And then you need to wind the clock 30 years forward and say, okay, where are those same features and continents and highlands and lowlands now? Right? And if you don't have an exact estimate of Venus's rotation rate, you don't know exactly where those features are. You may think, okay, I'm going to put this lander on a mountaintop, and if your estimates are wrong of how much Venus has rotated since the last time we mapped it, you may end up landing it in a valley, which is fine, or a lowland. Great, you can still do science if it's flat. What if you put it on the side of a mountain, and then all of a sudden your really expensive lander that's been armor plated and made with crazy alloys to withstand 500 degrees Celsius worth of heat basically lands on Venus and goes tumbling down a slope and dead within minutes. All right, so you see the nature of the problem here and why it's been so tough to study this planet all this time. It's shrouded in secrecy. It's got this mystery. It's got this, we think we should know it well because it looks and feels and all of that so much like the Earth, and yet we don't. Kind of frustrating. It's time for you to call your congressperson and say, send missions to Venus. Fund them, damn it. All right, so that's what I'm trying to get at over here. All right, so coming back to this, so Venus is about 70 to 75% lowlands, consisting of basaltic lava, which is kind of like we see under the ocean on the Earth, and also similar to Lunar Maria. There are two areas of highlands. So one is called Ishtar, which is one on the top, and Aphrodite, which is on the bottom, and gives you a rough idea of where it is on the surface. Not that you might have an instinctive idea of what is going on. And there don't seem to be plate tectonics because there's no water and so on. Actually, why am I putting that in here? Okay. Rotate slowly. Wind speeds are probably not that fast, so not that many wind-blown features. No water, no ice, low wind speeds. So erosion is probably not that much of an issue on Venus. I'll say probably because we'll study some of it later on. And no plate tectonics. Okay, so of the three remaining, impact cratering, volcanism, and just regular tectonics, what's left? Well, I'll give you the answer right away. Here's a 3D image of Venus's surface. It was kind of generated by artificially stretching NASA's Magellan radar data. And so what you see over here is a 3-kilometer tall volcano in the background, which is called Gula Mons, that's on the horizon. So 3-kilometer tall is about 3,000 meters, 10,000 feet, just for reference. So we're talking about lower than Mount Shasta. Mount Lassen is about 10,000 feet, and that you can hike to the top of and back. Half Dome in Yosemite is about 8,000 to 9,000 feet tall. Okay, so that's the kind of height we're looking at over here. And in front of it, you see a 50-kilometer, so that's about 30 miles, so 48 to 50 kilometer wide crater at just right of center. Okay? So, one thing, if you remember back from the Earth chapter, and I've told you now 2 or 3 times that there's no plate tectonics on this, if there are no plate tectonics, that will affect the types of volcanoes that there are on a planet, right? Remember that the Earth has this ring of fire where oceanic crust is diving under continental crust, and so very close to the surface, there's friction between rocks, magma builds up, and it comes out as volcanoes along the coast, like the Cascades over here, the Aleutian Islands, the volcanoes in Japan and Chile and the Philippines and so on. And you see that in a bunch of other places. New Zealand has them and all that. There's also hotspot volcanism in Hawaii, where there's no plate boundaries. That's dead center in the middle of an oceanic plate. But plate tectonics is carrying these land masses over a spot where magma is coming out from the center. There's some weak spot over there or whatever. Iceland is one such place as well, where, and there are islands in the Indian Ocean that are like that as well. But basically, there's a conveyor belt moving land masses over a hotspot, and magma is coming out and adding to them. So Kauai, which is the northernmost, actually, north of Kauai, there's a whole chain of submerged former volcanoes, extinct volcanoes, that used to be over the hotspot, have moved on, and then eroded away because of wind and water. Kauai is the most eroded and lushest island, the most lush island, because there's more soil on it and so on. And compared to the Big Island, which is the newest island, parts of the Big Island are still being made. 2 years ago, Kilauea erupted. They added a few hundred square meters to the southern side of the island. The next Hawaiian island is not that far below the waves. In the next, 10,000 to 100,000 years, there will be a new Hawaiian island. As the Big Island continues moving northwest, there'll be a new island, that, new landmass that will end up over the hotspot and start getting built up, and you'll end up with another island south of the Big Island. Okay? So again, that's all driven by the movement of the Earth's crust, by plate tectonics. In the absence of that, what are your volcanoes going to look like? All right. So, why do we know that impact cratering is the second most important? Like I said, the surface has been resurfaced. Volcanism is the only thing we know of that could do a bulk resurfacing or a bulk remodel of your planet, if you will. And so there's not that many craters that we find in the radar mapping of Venus because they have been covered over by lava and so on. Okay, so let's take a look at what the major geological features are. Here are some really interesting features that you don't see on Earth. So Venus has these things called coronae or crowns. They're ring-like structures that range from 100 to 1,300 miles wide. So it may be because hot material beneath the crust came up and warped the planet's surface, as opposed to what we see on Earth, where we have plates smashing up against each other or spreading or going under each other and so on. So Venus has these things called coronae or crowns. It has something called tesserae or tiles, which are these raised ridges and valleys formed in different directions, and we'll go over them in some amount of detail. But before we take care of volcanism in depth, let's go in order. We had cratering, volcanism, tectonics, erosion. We said erosion, probably not that much, but let's take a look at cratering on Venus. Okay, there are impact craters. We saw an image of one previously, but it's no significant craterings, definitely not as much as the Moon or Mercury. And all the craters are large. There are no small craters. I'm going to give you a minute to think about why there may not be small craters. What happens when a meteor, an asteroid, comet, whatever, enters the atmosphere? When you look up at meteor showers, what are you seeing when you see shooting stars on Earth? Okay? So if you can see shooting stars on Earth, and Earth's atmosphere is not that thick compared to the Earth, thickness of a dollar bill and so on, if you reduce it to the size of an apple. We went through that exercise a couple of lectures ago. What happens when you're on a planet that has an atmosphere that's about 3 times thicker than the Earth? And now you'll sort of start figuring out why it is there are only large craters on Venus's surface and no small ones. So there are very few that are less than 10 kilometers or 6 miles in diameter, which means the rule of thumb is if you have a 10-kilometer wide crater, then whatever caused it has a diameter maybe 1/10 of it. So 1 kilometer in diameter object has hit the surface and created the crater. What happened to all the ones that are less than 1 kilometer in diameter? Okay. Second thing related to this is that, we can age a surface based on how many craters are there, because the bulk of cratering happened before 4 billion years ago and probably stopped about 3.8 to 3.9 billion years ago. This is a clue we got from the Moon, where the highlands have very, very different cratering than the Maria. And the Maria formed only about 500 million years later than the highlands. So we have a very precise timeline of when there was intense cratering and impacting going on versus when there was not as much going on by a large degree. So we can age surfaces based on crater density, and from the crater density, we can tell that Venus has not had, the surface is no more than a few 100 million years old. 600 to 700 is what we think it is. So it's, it's mostly covered by these flat, smooth plains where there's thousands of volcanoes, some of which we think are still active today. We'll go over the evidence for that later on in the lecture. And there's long, winding lava channels and so on. But it's a young, geologically active surface, and we know that from the crater counts. Okay. So in addition to not having that many craters, only having large craters, the other interesting thing is that there's a lot of double and triple craters close to each other. So if only things that are 1 kilometer or larger are hitting the surface, what's the additional thing that's happening to them? What happens to things that are 5 kilometers or larger, you think, when they're passing through the Venetian atmosphere? Okay, they're breaking up in the atmosphere, and so that's why you end up with 2 or 3 craters together. And a lot of these craters look fresh. There's very few signs of erosion. Does that make sense? What causes erosion on Earth? Like if you think back to the comparison we did between the Arizona meteor crater and a crater on Mars, for example, what was the difference between the two of them? Okay, so not too much cratering, implying that the surface is largely recent, not too many small craters, and craters sometimes come in 2s and 3s and so on. So that's cratering on Venus. Let's move on to the major factor surfacing Venus, or impacting how the surface, I keep using the same words, affecting how the surface appears under radar and so on, and that is volcanism. Volcanoes on Venus. That would be a cool band name. If any of you decide to take that up and form a band with that name, I'd expect, if not a royalty payment, at least a little bit of a shout out saying, yeah, this crazy astronomy teacher basically suggested it, or whatever. Okay, volcanism, dominant geological process on Venus. Because of the recent resurfacing, that's the only thing that can do a planet-wide resurfacing. And so the question is, how is this different from the other terrestrial planets? Do you think volcanism is dominant on any of the others? And is it so dominant, or as dominant as it is on Venus? So here's a radar image, again, of the surface of Venus. Bright means rough. So over here, young or recent lava flows, especially if you look at images of Hawaii, for example, recent lava flows tend to be rough. And then once erosion takes over from whatever process, they're weathered either through reaction with the atmosphere or with just wind and water erosion, if there is wind and water. So the question is, from what you see in this picture, are these lava flows young or old? The second thing that when we talk about volcanoes affect the atmosphere as well. They outgas carbon dioxide and another gas called sulfur dioxide, which is sulfur with 2 oxygen atoms attached to it. And you can track the concentration of that. So that's something we do regularly on the Earth. So when Mount Pinatubo in 1990 erupted, its eruption basically carried gas and dust and ash all around the Earth, and we could also measure sulfur dioxide all around the Earth. Sulfur dioxide is kind of interesting. It's almost an anti-greenhouse. Some of the aerosols that volcanoes put out reflect sunlight back, and so they cool the planet. So after Mount Pinatubo erupted, for about a couple of years, temperatures are a little lower around the planet than usual, despite the general warming trend that had started slightly just before then. Okay, so there are detections of hotspots and changes in sulfur dioxide composition. Is there anything else I wanted to say about this? No. Okay. So a combination of different lines of evidence. One is when you do a radar map, you can also do things like take the temperature of the atmosphere and the terrain under it. And when you overlay a temperature map on top of a contour or topographical map, then you have the picture on the lower right, which shows high temperature material above a prominent mountain-like feature. The other thing was how exactly, well, so the timing, okay, fine. You have a hotspot, and that could be coincidental. How do you know that it is lava that is producing the heat and not just some random spot that happens to be over a hot spot on the crust for whatever reason, some weakening in the mantle or whatever? It could be hot but not volcanic. And the evidence for that actually came from a test done many years later, actually last year in 2019, on a lab on Earth where they recreated conditions like Venus, the crazy atmosphere, the really thick atmosphere, the corrosive atmosphere, and then simulated lava coming out and how it would evolve over time. What happens to how it flows, how it weathers, how the temperature should look if you were pointing a temperature probe at it. And they looked at what happens to how the composition of the lava changes. Certain volatiles will escape, the composition changes and so on. And they looked at it and they said, what we're seeing in these simulated lab conditions matches what we measured on a satellite that sent data back 15 years ago from Venus. And I can't spell. 15 years ago from Venus. And so that's how they said, this is a pretty good indication that it's a signature of an active lava flow, not just a random hotspot. The second thing they could measure is go back to data taken on other satellites of sulfur dioxide levels in the atmosphere, outgassed by volcanoes, and there was a match with the timeline between when the satellite was passing overhead, radar mapping, taking temperature, and measuring sulfur dioxide levels as well. And they put all those pieces of evidence together and said, not only has the whole planet been resurfaced in the last 600 to 700 years, 600 to 700 million years, these lava flows are actually just a few years old, so they've happened relatively recently. Now, in geological time. Forget relatively recently. So, like I said, given the different conditions, no plate tectonics and all of that stuff, what are the volcanoes like on Venus? And the answer is they're pretty damn weird. There are structures that are unique to Venus. So this is something called a pancake-shaped volcano. They're circular domes. They're not shield volcanoes. They're not stratovolcanoes that you see over here. But they're really wide. 25 kilometers tall, wide and only 2 kilometers tall. So it's extremely thick lava that is spreading out evenly. And we don't think they're actually basalt. So again, strange volcanoes on Venus that you don't encounter pretty much anywhere else in the solar system. The second thing I mentioned earlier was these coronae or crowns. There are sort of these fractures in the crust of Venus that are round, and they're visible from in radar data as well. This one is called the Miss Piggy one because you could sort of imagine two eyes and a snout over here, maybe even a couple of, 1 year. I don't know what their second would be. But, yeah. So this, in fact, what would be the left ear is a pancake volcano over here, according to this. So again, something that we don't see elsewhere. Why do we think these happen? Because there's no movement of the crust. So any hot rocks that come up from the center of the mantle, like on Earth, basically, and remember, the surface itself is extremely hot, 460 degrees Celsius. So any rocks that might have lead or something on them are actually already pretty deformable, meaning they're pretty close to their melting point, and so they can deform and flow around a lot easier than rocks on Earth, where it tends to be close to the freezing point of water, and so on. So these plumes of magma, we think, rise to the surface and form these coronae, and here's a schematic showing you how exactly that happens, where there's partial melting underneath the lithosphere, and then it sort of starts spreading out sideways, compressing the crust as it goes forward, and those compressions are equal in all directions, and which is why you end up with these circular features and these lines along the edges of the compressions and so on. And so there's a ring or an annulus, as it's called, and in the center of it you have a little bit of a central rise, which may look like a pancake volcano actually. There's also regular volcanoes, like this volcano called Mat Mons, which is about 5 miles high, which is the height of Everest, roughly. There's one in the and again, lighter color means rougher, which most likely means recent lava flows from the mountain. And here's a close-up of the one in the distance of Mat Mons and the lava flows coming off the flanks of that. This has been heavily exaggerated vertically, but these volcanoes wouldn't really stand out from the surface that much because there's mostly gently, sludgy lava, gently rolling terrain all over Venus. Okay, so not only is, well, you could almost say that one measure of the fact that volcanism is more dominant on Venus than elsewhere is the fact that it has these really unusual volcanic structures that you don't see elsewhere. Maybe a bit of a weak inference to draw, but because of the lack of plate tectonics and because of the extreme heat and the crazy atmosphere of Venus, which we haven't even got to yet. Maybe I should have done the atmosphere first. Okay, so that's cratering, that's volcanism on Venus, both highly unusual and nothing like we've seen on any of the other planets so far. Okay, how about tectonics? These, again, there are no plates, so these are just happening in the crust. They're not, it's basically just a stretching and compressing of the crust. So this we've seen on Mercury, on the Moon, and even on the Earth. So the other thing, of course, the thing here is that the fractures are often near volcanoes because there are just so damn many volcanoes on Venus. So you could spit a ball of lava from a volcano and basically hit a compression or a tectonic feature in the crust of Venus. Okay? But there is no slipping and sliding, there's no smashing up against each other. It's purely forces from within Venus causing stretching and compression of the crust. And so one of the reasons why we think there is no plate tectonics is that you don't see dramatic features like you see on the Earth that are the result of plate tectonics. So plate tectonics, remember, has 4 ways of affecting, when they smash up against each other, you get really tall mountains like the Alps and the Himalayas and so on. When they spread apart, you get these dramatic rift valleys like in Africa or at the base of and mid-ocean trenches and so on. When they slip and slide, you get things like you see in the Carrizo Plain, or you see these long linear structures on the Earth's surface like Tomales Bay or Crystal Springs Reservoir, which is big long structure. And the fourth thing is when you have subduction, then you get rings of volcanoes where ocean and continent meet and so on. You don't see any of that on Venus. It's all surprisingly flat, gently rolling hills. Like I said, all these pictures are pretty exaggerated vertically. This is closer to reality, where you have these gentle rises. Like I said, the Pancake volcano is 25 kilometers across, only 2 kilometers tall. So really, really broad, but not that tall. Okay. So there's still a few highlands and there's large volcanoes 5 miles high and so on, but there is no evidence of crustal plates. There's lots of cracks and ridges, but they don't all link up to form one big circular, or at least they don't close in on each other to form plates like you see on the Earth's surface. That said, the 2 major continents, Ishtar and Aphrodite, that I happened to mention before, were formed by were formed by tectonics, not plate tectonics. So the uplift of those 2 big features, what we call continents, surrounded by all these lowlands, the planetias, as you see over here. So Ishtar and Aphrodite were caused by tectonics, which is caused by convection currents in the mantle. Where the convection currents come towards each other, you get compression and things get pushed up. Where they're spreading apart from each other, you get valleys and lowlands. So this is the Earth, where in addition to those convection currents, you also have subduction, which is lubricated by water at the ridges, and new crust is being formed at the mid-ocean ridges, where part of the carbon cycle and so on. So this is on planet Earth. And to contrast, notice on Venus, First of all, the crust is plastic. Plastic just means it can be deformed. It's hot enough that it can be, like I said, 460 degrees Celsius surface temperature of the atmosphere, 460 degrees. Imagine what the temperature of the ground must be. And so you just have the conventional things over here where you have upwellings, you have volcanoes, where you have downwellings, you have pileups and stuff like that. So there's not as much sideways motion because of the absence of water, unlike in plate tectonics on the Earth, where you can have, half the width of the Pacific Ocean is basically moving. It's getting pushed away from the center of the Pacific, and the edge of the Pacific is being pushed under crust. So that's a huge amount of material in motion together. And there's none of that on Venus, which is why you end up with these fairly plain vanilla tectonic features because of the absence of water and the heat of the crust itself, making it more malleable, as they call it, which means it can be moved around. So the signatures are there for tectonics, but for a planet of its size and the amount of internal heat that it has, and especially compared to Earth, because we do that a lot, there's just nothing that looks anything like the huge tectonic features that you see on Earth. But they're there. So volcanism dominant, cratering, yes, some tectonics, yes, some. But and the evidence is there on the surface of the planet. All right? So I'll let you read about the Lakshmi plains of Venus and where are they? They are, I saw them. Oh, there, to the left of Ishtar on the top left of the picture. So again, close to volcanic features, which are on these highlands and so on. Okay, here's another instance of a crater, but then tectonics later on modifying the appearance of the crater. So what you have over here is basically it landed, the impactor itself landed on a place where this was happening, where there was a convecting, a mantle current directly underneath it and causing all kinds of things like a fault, which almost destroys half the crater and so on. Okay? So then the question is, now you see a relief map that looks like this, with highlands and lowlands. The natural question to ask is, well, did this planet at any point have continents and oceans? Okay? And the answer is maybe. We'll get to really recent work. In fact, an article that came out just a couple of weeks ago that I'll talk about at the very end of this lecture, which comes to the surprising conclusion that Venus had not only surface water, but had surface water for 3 billion years, way longer than Mars might ever have had it, and comparable to how long Earth has had it. But it's all gone now. And we'll walk through that scenario. It's kind of a compelling argument that ties together a lot of the things that we'll put together in this lecture, but it's kind of cool. Okay. But what we're seeing here is a thermal imaging spectrometer that basically detects infrared radiation given off by various surfaces on Venus on the nighttime side of the planet in the southern hemisphere. So 75% of the surface is low-lying basalt like the oceans. That's one clue. But there's no evidence of subduction. So these are probably more like lunar Maria, where it's just lava from convection and not from oceans, continents, and plate tectonics, and so on. And on the Earth, the other thing is that the continental crust is lighter than oceanic crust, and so the oceanic crust, again, being denser, can dive underneath the continental crust. We don't know if there's this density differential here as well to cause that kind of stuff. So maybe the highlands are only produced by volcanic activity. So the answer to whether or not Venus has plate tectonics, just to wrap up this tectonics section of the geological part, doesn't seem to be in action. because the water is gone, and there's nothing to lubricate the motion of one part of the crust over the other, and so on. So the planet, we think the crust extends over the entire planet and basically just has weak spots and hot spots and so on, where it is sitting above either magma or it's sitting above mantle convection currents, which may be one and the same thing in some places. Okay. Moving on. This is a photo that we saw from one of the landers early on in the lecture. Let me bring it up again. These are two different lander pictures. Yes, they're in two different parts of Venus. There doesn't seem to be much evidence of erosion, either water or wind. Okay, that's because the planet has extremely slow rotation, so there's pretty slow winds, there's no rain, and so all of this resurfaced lava has been weathering probably because of chemical weathering and not because of erosion like you see on the Earth. So it goes from lighter in color on those pictures to darker later on because of chemical weathering and so on. So very little actual erosion. Okay, so to summarize, there is cratering, volcanism, tectonics, but way more evidence of volcanism than there's way more volcanism than cratering and tectonics. Cratering we know because we can date a surface based on the number of craters in it. There's tectonics in the sense that there's compressions and depressions and so on and fractures in the crust, but no plate tectonics, probably related to its dryness. And to know more, we should probably be sending more missions to Venus, but we'll talk about that. There's only been 3 in the last 30 years. I think a couple more are planned. We'll talk about the atmosphere of Venus and how, as crazy as it might seem, there may actually be places where life may be able to exist, even though it's a completely hellish atmosphere, filled with sulfur and sulfuric acid clouds, if you can imagine that. Right, so we'll cover 2 different aspects. What is Venus like today? Short answer, absolutely hellish. And the second thing is, how did it get so hot? Is there a cautionary tale over there for us? It's improbable, but there probably is a cautionary tale of some kind. We went through the scenario when we talked about the Earth's atmosphere, about what would happen if all of the carbon dioxide dissolved in the oceans were to end up in the atmosphere. The atmospheric pressure would go from 1 atmosphere to 30 times, because basically all of that water vapor would just add... if all of the carbon dioxide... Wait, what did I say? Let me think about this. Yes, if all the carbon dioxide dissolved in the oceans and all the water basically ended up in the atmosphere, you'd end up with 30 times the atmospheric pressure and way hotter temperatures. And then what would happen if all of the carbon in the rocks ended up in the Earth's atmosphere? You would basically end up with 90 times the atmospheric pressure, or 100 times the atmospheric pressure, which is Venus. Okay? So that's what Venus is like today. 96% carbon dioxide atmosphere. No evidence of water on the surface, no evidence of water vapor. Most of the rest, 96% carbon dioxide, most of the rest is nitrogen. 90 times the atmospheric pressure of Earth. So the troposphere is huge, 5 times the depth of the Earth's. Earth's is 10 kilometers tall, which is pretty much the size, the height of Everest or so. Slightly more than that. But this is 5 times taller than that, which is, roughly where our stratosphere is considered to end, is where Venus's troposphere ends. Okay. There's a lot of sulfur there, which is why I keep using the hell analogy. It's sort of, I guess, the Christian conception of hell. There's, because of volcanoes in the last 600 to 700 million years, probably active volcanoes now. The atmosphere has an effect on the way the whole surface appears, and you saw that in the early picture where it looks all yellowish up here. So there's this yellowish cast to the atmosphere. And so when landers on Venus took photographs of the surface, you basically had to have a color calibration bar and then shift the color so that it would look like it was lit on the Earth. So it's a rocky surface, permanently overcast skies, At the right-hand top corner of this picture, you can see a little bit of the atmosphere. Again, it looks as yellow as it was. The light of the sun is scattered. It scatters more wavelengths than just the blue. So the sun basically appears reddish or yellowish. And so, when you get it back to Earth-like conditions, you can see that the bottom picture looks like basalt or lava. It looks like the gray of the moon and the Mercury surface, which is what you might expect for fresh lava, which is how, again, we concluded that, this looks like a lava plain that has recently been resurfaced. Okay, any other objects in the solar system that are the same color? I just gave it away. Never mind. Man, I need to... Anyway. Okay, so we looked at this. When you look at it in the visible and the ultraviolet, you only get to see the upper cloud layer. But the strange thing is that, so Venus is rotating clockwise really slowly, goes around its axis once every 240 Earth days. But this upper cloud layer moves really, really rapidly in 4 Earth days and opposite to the direction in which Venus rotates. So we don't completely know what is going on over here. So there's these rings of polar clouds, and there's this weird V feature, as you can see, in the clouds. We don't have a very good understanding of what all of that is. Why the upper atmosphere is rotating around at these crazy wind speeds and in the opposite direction, we have no real clue yet. We do know that on the surface, there's hardly any wind because we've sent landers down there and taken wind measurements and so on. Okay. Some of this is recap. You know that it's 96% carbon dioxide, 90 times the pressure of the Earth. It's the same as being 1,000 meters down in the ocean. So just for reference, 1,000 meters down is about 3,000 feet. Most submarines and stuff, I think, dive to depths of a few hundred meters or so. Okay. At the surface, the slow rotation produces very little weather. The winds are only about 6 kilometers an hour, which is kind of a gentle breeze, maybe even less than that. And so as a result, there's not a lot of wind erosion that takes place on surface features, or at least if it does take place, it takes place over a really, really long time. This thick carbon dioxide atmosphere obviously has an extremely strong greenhouse effect, as you know now. And why isn't the Earth like this? Because most of the Earth's carbon is locked away in the ocean, and in the ocean and rocks. The larger portion of it is in rocks and the mantle than is in the ocean. But if all of it were to get released, so somehow or the other, then you could end up with Venus-like conditions on the Earth maybe several billion years from now or so on. Okay, because Venus doesn't have much tilt, because it rotates so slowly, there is not much variation in temperature between the equator and the poles and the day and the night, because the atmosphere does a really good job of just redistributing heat. So this is different from, you don't need actual molecules to be moving. They can be exchanging. They can just be jiggling and exchanging energy with their neighbors, and then that just redistributes across the entire planet. So there's not much difference in daytime and nighttime temperatures, as you might look over here. Average surface temperature is 460 degrees Celsius. Not much change, unlike the moon and Mercury, which had dramatic 300 to 500 degrees Celsius variations between the day side and the night side. There is not as much on Venus. Even the Earth has some amount of variation between the day side and the night side. If you've been through heat waves, even in California, temperature does go down by about 20, 30 degrees Fahrenheit. So it's kind of interesting. That does not happen on Venus. Okay, what about above the surface? So we've talked about the upper cloud tops, which we can see. We talked about the surface, where we have some example of. What about everything in between? Okay. Lots of carbon and nitrogen that I said, but about halfway up, from 30 to 80 kilometers, there's all this haze, which is caused by droplets of sulfuric acid that form clouds up there. And any remaining water that happens to be on Venus is basically locked up in sulfuric acid. So water plus sulfur dioxide basically gives you sulfuric acid, H2SO4. So, well, it's H2O plus sulfur dioxide plus some other oxygen when water is dissociated, gives you sulfuric acid, and that's where we think all of it is locked up. Unlike the Earth, which has this crazy distribution of temperature, in the troposphere, it behaves like Venus does over here, where the temperature is highest close to the ground, and then basically drops as you go higher in altitude. Then once you get to the stratosphere, strange things happen. As you go higher in the stratosphere, the temperature starts rising because of ultraviolet absorption by ozone, and then it starts falling again. And then you get to the thermosphere and the exosphere, where the temperature starts rising yet again. All that strangeness does not happen on Venus. You just have this uniform, straight up. As you go further up in the atmosphere, temperature decreases, density decreases as well. The interesting thing to look over here, the bottom temperature scale is in Kelvin, which I apologize for. Should have done temperature scales early on in the class, note to self. But somewhere around the 50 kilometer mark, you'll notice on the right side, it shows you pressure in atmospheres, Earth atmospheres, and the 1 atmosphere pressure level is 50 kilometers up. And coincidentally, if you follow the temperature curve as well, at the 50 kilometer point where the pressure is 1 atmosphere, the temperature is around 300 to 350 Kelvin, which is room temperature on Earth, roughly above the freezing point of water. So there is the not too crazy idea that life, if it exists on Venus and it's Earth-like, there could be bacteria floating around at a height of 50 kilometers in these acidic clouds, living under 1 atmosphere, Earth-like atmospheric pressure and Earth-like temperature. Not a completely crazy idea. So one of the ideas for a mission to Venus is basically saying, okay, what happens if we were to send a balloon into the atmosphere and have it just be buoyant at that 50 kilometer point? And then we start sampling the atmosphere at that point to see what it's like. Maybe we could even have floating hotels in the atmosphere of Venus, where you step out on a balcony, in a spacesuit and with oxygen and so on. But you could split apart sulfuric acid to get water, and you could get oxygen out of that too, and so on. Talk to a billionaire with a big ego that's not Elon Musk, maybe Jeff Bezos or someone, and say, hey, Elon's going to Mars, why don't you go to Venus? And have I got this crazy idea that I heard about from this insane astro teacher in a class that I took? So there's something you could try and spark in somebody. Okay. So 96.5% carbon dioxide, most of the rest is nitrogen, pretty much no free oxygen or water in terms of water vapor and so on. No ozone, so no stratosphere. We think the sulfuric acid and there's a continual source. The reason that the sulfuric acid clouds never go away is that they're constantly being replenished by volcanoes. And so despite being as thick and crazy as it is, relatively simple atmosphere compared to the Earth. So pretty straightforward relationship between temperature and pressure and altitude and so on. But possible. Life may be possible up there. Okay. I had shown you a picture of the complex circulation patterns on the Earth, partly because of the Earth's tilt and because of its atmosphere and so on. Because Venus is not tilted and because it's relatively uniformly the same temperature, there really is not much of a circulation pattern in terms of wind as you see on Earth. So there's just 2 slow convection cells. Well, actually in the upper atmosphere they're pretty fast. But there's basically 2 convection cells just carrying heat away from the equatorial regions into the polar regions, which have less direct rays from the sun. Pretty simple. So I'll just leave it at that on the slide. And that's something you can go over. So then the question arises, how did Venus get to be how it is, how we measure it to be today? And that's an interesting story and a cautionary tale in some ways by itself. Okay, so let's step through this climate history. Venus may have been once like Earth because it started from the similar initial conditions, a ball of gas and dust and rock, not too far from the sun, at a place where water could, at the edge of the habitable zone, where liquid water could have existed under the right atmospheric conditions. We will never know because any rocks or fossils or anything are all gone because of all the recent resurfacing. Unlike Earth, where you can find 3.5–4 billion year old rocks that have been dredged up from the inside or wherever, it's unlikely that we would find that. I mean, it's hard enough to find on the Earth. Imagine on an alien planet with hellish conditions where we don't even live on the planet, trying to find rocks that date back to Venus's formation. Very hard to find, especially because there's new material being dredged up with lava flows all over it. So we think early Venus may have had an ocean about 2 billion years ago, probably had a similar initial atmosphere, which was outgassed from volcanoes like it was on Earth. Basically water vapor, carbon dioxide, sulfur dioxide, and so on. Remember, oxygen was created by life on Earth. Basically, it's a waste product of life. And as life reinforced itself, there was more and more oxygen being pumped out by cyanobacteria, or basically bacteria that could use photosynthesis to take carbon out of the atmosphere and send oxygen back out. So Venus also is closer to the sun, so it probably got a little more heat. Any carbon dioxide basically started absorbing more of that heat and caused a hotter atmosphere as a result. And so more water vapor ended up in the atmosphere, and then that becomes a feedback loop. So similar amounts of carbon dioxide as the Earth, but slightly closer to the sun. So more heat trapped in the atmosphere by the carbon dioxide means more water vapor goes up into the air. Water vapor is also a greenhouse gas. Was probably no water cycle or deep carbon cycle to take that carbon dioxide out of the atmosphere. So basically just, positive feedback loop that just fed on itself and evaporated all of the oceans and drove all the carbon dioxide out of the rocks and out of any oceans that it might have had, obviously, into the air. And once water vapor was in the air, essentially it could get dissociated into hydrogen and oxygen. The hydrogen is a really light element. It just bubbles up to the top of the atmosphere and just leaves. Venus does not have much of a magnetic field, so all of that is just getting stripped by the solar wind at the top of the atmosphere. And oxygen is highly reactive. So it can react with sulfur dioxide and any leftover hydrogen that didn't escape and form sulfuric acid like we see today. Okay? So basically, once water vapor started leaving the oceans and the oceans evaporated, all bets are off. The thing just went crazy. And the Earth has roughly as much carbon in its rocks and in its ocean as Venus has in aggregate, but all of Venus's is in its atmosphere as a result. So two completely different evolutionary paths based on proximity and some other factors, like maybe plate tectonics never got going, so a carbon cycle never got going on Venus as well. What else do I want to say about this? And of course, we won't completely know the truth, like I said, even if we put landers there, because of the surface is only 600 to 700 million years old. Right. So on Earth, any water and carbon dioxide and sulfur dioxide that comes out of volcanoes gets recycled. The water vapor comes down as rain. It can dissolve the sulfur dioxide and the carbon dioxide and carry it with it into the oceans. The water also causes weathering on the surface, so rock basically and soil and so on gets washed into the ocean, down into the base of the ocean, sedimentary rocks form, they get subducted into the mantle and then come back up through volcanoes or mid-ocean ridges and so on. So there's this big water, carbon, and sulfur dioxide cycle, which does not exist on Venus, or we don't think it ever existed on Venus, and so that's why it ended up the way it did. Basically, any water vapor, carbon dioxide, and sulfur dioxide went straight into the atmosphere and stayed there. Because there are no oceans to dissolve any of the carbon dioxide, it basically traps more and more heat. If there even were any oceans to dissolve, they would have, they've possibly evaporated because of the amount of heat. 460 degrees Celsius is well above the boiling point of water, even under ridiculous amounts of pressure. And so some of basically the H2O and SO2 formed sulfuric acid. The remainder that didn't form sulfuric acid was broken apart without ozone to absorb ultraviolet radiation. The water absorbed it, split into hydrogen and oxygen. The hydrogen went away. The oxygen got locked up in rocks or in more carbon dioxide and sulfur dioxide and so on. And so that's why we ended up with a runaway greenhouse effect on Venus that essentially took its surface temperature from what might have been very similar to the Earth, and instead of stopping after about 30 degrees worth of warming, which the Earth's atmosphere provides, basically gave it 400 plus degrees Celsius of warming. And with no carbon in any of the rocks, there's no oceans to hold carbon as well. This is taken from the book, and I just wanted to put this over here to show you that this is kind of wrong, because it depends on how you define the stratosphere. I think the book has a little bit of a wishy-washy definition of it. Maybe they consider the stratosphere anywhere above clouds, so all the clouds on the Earth occur in the troposphere and none in the stratosphere. So I just wanted to point out that the book may say stratosphere, but there is no ozone over here on Venus to call it a real stratosphere. Maybe if you consider the stratosphere where ultraviolet radiation gets absorbed, then yes, this is the stratosphere, because sulfuric acid or any remaining water molecules are the ones that are doing the absorption. But the clouds are close to the top of the troposphere, which is about 50 kilometers up, like I said. It's the part of the atmosphere where convection currents can be set up. So the hottest part is near the surface. It cools a little bit at the top, and you can set up convection currents and have some weather, even though on Venus it's really weak. So you only have 6 kilometer per hour winds and so on. But in case you get confused, I just wanted to put this over here and clarify what's going on in this slide versus what's being said in the book. Okay, so this is again going through the relative scenarios. Similar initial conditions for Venus and the Earth, except Venus is slightly closer, so it gets a little bit more sunlight, and that kicks off this runaway greenhouse effect, and Venus ends up looking and feeling like hell. Can this happen? Are we at the point where we could be changing the Earth's atmosphere irrevocably? We're still a long way off. We still haven't dumped enough carbon into the atmosphere to get to the point where this kind of nightmare scenario could play out. But we're on the path. And at some point, we need to get off that path, because as it is, life is getting pretty unbearable for people in developing countries who have to deal with record heat waves or have to deal with disappearing freshwater sources and so on. So this is the nightmare scenario. We're on the bad dream scenario right now, but we're on this path. Okay? And so here is something where you can, why is Venus hotter than the Earth? You know the answer to this question. I am not going to spend too much time on it. And we will do a quick summary of what Venus is like today. Ridiculously thick carbon dioxide atmosphere, no water vapor in there. Any water that's up there is locked up in sulfuric acid. Relatively uniform temperatures all around. There's just 2 slow convection currents. There's slow rotation, so there's not a whole lot of weather. Though the upper atmosphere goes in the opposite direction and much faster. We don't know why. There was this crazy runaway greenhouse effect that made Venus too hot. So that's why all the water is gone. And 460 degrees surface temperature. So that's a review. Now, here's something that argues that Venus might have been habitable for a really long time. that from 4 billion to 1 billion years ago, there was surface liquid water and a nitrogen-dominated atmosphere like we have on Earth now, the so-called temperate period. The 600 to 700 million years from in the past from now was the resurfacing period that we know about from the data that we see on the surface. So this is putting together a whole bunch of pieces of evidence and coming up with the fact that in 1 billion years, Venus may have gone from being a pretty balmy place where we could have vacationed to absolute hell. And that basically happened during the course of something called the Large Igneous Province period, where coordinated volcanic eruptions, maybe planet-wide, continent-wide eruptions, ended up pumping ridiculous amounts of water vapor, carbon dioxide, and sulfur dioxide into the atmosphere at a fast enough rate that if there were a water or carbon cycle that might ever have existed on Venus, it couldn't deal with such huge amounts of greenhouse gases being pumped into the atmosphere. And something like this has happened on Earth. For the longest time, there was dispute over whether it was an asteroid that killed off the dinosaurs or it was volcanic eruptions that basically created a global winter, in the sense that all these aerosols spat out by, this is the particulate stuff, not carbon dioxide, sulfur dioxide, all that stuff. I mean, there is sulfur dioxide. Sulfur dioxide creates this haze, which can cool the surface of the planet enough that basically photosynthesis, or blocks out the sun enough, that photosynthesis shuts down and your food chain dies out. Meaning all the dinosaurs that fed on plants died, then all the carnivorous dinosaurs that eat the herbivorous dinosaurs died, and mammals managed to live on dead or decaying organic matter or whatever it was that they lived on underground and survived until the Earth warmed up again and photosynthesis could kick in again. So this has happened. And there is an area in India called the Deccan Plateau, or the Deccan Traps, which is a huge plateau of basalt or lava, former lava, cooled lava, that we think was caused by a huge eruption, simultaneous eruption by multiple volcanoes in that area about 65 million years ago, which is why for the longest time there was this dispute of whether it was the volcanoes or the asteroid that killed the dinosaurs. Now we've got better evidence. I mean, then for a while people thought, what if it was both? Maybe the asteroid hitting the Earth, just like the Caloris Basin on Mercury affected the other side of the planet, maybe the asteroid hitting one side created all these planet-wide tectonic disturbances and ended up causing the lava, So there was enough uncertainty in the volcanic eruption timeline to figure out, maybe there was a problem. And it's possible that there was a little bit of both involved. Like we now think that the volcanoes erupted first. So things were already kind of bad on the planet. Temperatures were low, photosynthesis wasn't happening as much, and all that stuff. So dinosaurs weren't doing all that well to begin with. And then the asteroid came and slammed into the Earth and basically finished the job. And here we are to tell the tale. So this LIP period is not completely, it's never happened on a planet-wide scale on Earth, thankfully. Who knows if it could happen again? I hope not. But the upshot of that is that, again, because Venus and the Earth started out with similar initial conditions, that Venus might have had because it doesn't have much weather, because of the slow rotation, it had a carbon-rich early atmosphere with just enough greenhouse gas to allow liquid water to form on the surface, and that stayed stable for 3 billion years. Okay? So how do they know that this is a plausible scenario? Okay, so let's walk through this. Put together everything we've done in this lecture and relate it to the Earth stuff we've done early on. Okay? Let's see if you can follow me through this. If you can't, pause, rewind, slow it down, whatever. But it's a cool argument. Okay, so let's start with the premise that Venus had little to no life. So no life means no oxygen or ozone. So instead of breaking up ozone and forming oxygen and oxygen reforming to form ozone and so on, UV breaks up water instead. Okay? It's closer to the sun. So hydrogen and oxygen dissociate. Hydrogen escapes because there's no magnetic field on Venus, slow rotation, and there's more solar wind closer to the sun. So hydrogen goes to the top of the atmosphere. It's the lightest element, strips out. Okay, oxygen oxidizes the rocks, basically rusts them, and that's something we'll talk about on Mars, the reason why Mars looks red. Okay, as the water vapor goes away from the upper atmosphere, more water evaporates from the surface of Venus. Because the water vapor is up there, is doing the job that ozone does down here, and the ozone was produced by life, basically. Indirectly. First, there's oxygen that goes into the atmosphere from plants and so on, and then that forms ozone higher up. Okay, so the water vapor goes away until 99.9% of the water vapor is gone. So there's nothing to dissolve carbon dioxide and put it into rocks anymore. There's no carbon cycle. No water means no plate tectonics, means carbon dioxide starts coming out of volcanoes along with sulfur dioxide and hydrogen and water vapor. And this is what starts happening. You basically start with no recycling of carbon and a runaway greenhouse effect, and Venus ends up the way it is today as a result. So it kind of hangs together. It's kind of cool. So this positive feedback loop. So now all the carbon dioxide is in the atmosphere. All the water is gone. That's Venus today. How do we know that this might be a plausible scenario? One thing, if you think back to the lecture on atoms, is that hydrogen comes in isotopes. So just a regular hydrogen atom is just one proton and one electron. Simplest atom there is. An isotope of hydrogen called deuterium, or heavy hydrogen, is one proton, one neutron, and one electron. So that's double the weight of regular hydrogen. And suddenly it's not that light and takes more time than regular hydrogen to bubble up to the top of the atmosphere. So it's lost at a much lower rate than hydrogen. And you can measure deuterium has different energy levels than hydrogen. And you can do spectroscopy of the upper atmosphere of Venus, which has been done, and figure out the ratio of deuterium, or heavy hydrogen, to regular hydrogen. One proton hydrogen, as opposed to one proton plus one neutron hydrogen. And that ratio is high. So as a result of that, you can now work backwards and put the entire picture together and say, at some point, this is what may have happened, where Venus might have been actually habitable, quote unquote, for a long time. No one chose to take Venus up on the whole habitability invitation there. They're like, 3 billion years, come on, nitrogen in the atmosphere, water lying around, why the hell did no one show up? Luck of the draw. Maybe the meteorite that was supposed to hit Venus and seed it with life got deflected by Jupiter and landed on Earth and carried bacteria to the Earth, and they said, oh wow, this looks nice, let's hang out here instead and colonize this planet. Yeah, and if you have any more illusions about whether you're significant, the real rulers of the Earth are bacteria. They've been around for 4 billion years. You add up all the bacterial mass, there's way more bacteria than there is anything else. A lot of you is bacteria as well. Anyway, side note, whatever. So, not completely implausible that Venus was habitable in the past. And this is a paper that came out, I think they did simulations of Venus's atmosphere and basically said, here's how it might have gone from carbon dioxide dominated atmosphere like the Earth in the early days that warmed up Venus a little bit, enough for water to exist on the surface. Solar radiation was increasing. Like we said, we looked at long-term climate change things. Over 4 billion years, the sun has increased in brightness by about 30-40%, which is significant. Over a few 100 million years, it's only about 10% or so. So things can adjust. But carbon dioxide dominated to nitrogen dominated like the Earth, and then boom, planet-wide volcanic eruptions, and we end up with hell today. Pretty cool, huh? All right, I will leave you at that for Venus. The next lecture we will cover Mars, which is a fascinating body in its own right. Remember to tell your local favorite billionaire to send balloons to Venus so that we can look for life at the 50-kilometer mark, 50-kilometer altitude in its clouds, And if you use Volcanoes of Venus as a band name, I'd like to know about it. All right, take care.